All right. Oh, I don't need to talk so loud. Good afternoon, everybody. Hopefully there's not too much overlap with Jamin's talk. I'm going to be talking about error handling on the client side. So we've seen a lot of really cool JavaScript technology the last 2 days. But this afternoon I'd like to talk a little bit about what do we do when it all falls on its face. This talk is called Traces of Errors, and it's about first actually getting stack traces in your client-side code, and then getting better stack traces. But why is that important? Because whenever you're trying to show something awesome to your customers, to your clients, to your users, or to a room full of developers, inevitably, a large percentage of the time, it will blow up right in front of you. And it will blow up in very unexpected ways that may or may not tell you anything interesting about what happened or what went wrong.
Woo! I know that's about.
You can fix this one?
Yeah.
I get this all the time.
Especially when you minify your JavaScript.
Yeah. So errors are inevitable. They're usually costly, often embarrassing. But if we take a little bit of time to instrument our client-side code and expect that errors will happen and get better information about them, hopefully we can feel a little bit less like, and maybe a little bit more like. So let's talk a little bit about error handling in the client side. I'm Todd Gardner. I'm from Minneapolis, Minnesota, so it's way warmer here than where I'm from. I'm a co-founder of a company called Track.js, which is a client-side error handler, if you're looking for one. I tweet at Todd H. Gardner, sometimes angrily about JavaScript things that I don't like, so feel free to heckle me there. All right, so here's what I want to talk about today. First, some basics about the JavaScript error object in the browser and how it was implemented over and over and over again. And then we'll talk about the paths that errors take through client-side code, which are sometimes unexpected to people who don't primarily program in JavaScript. And then we'll talk about some custom paths that we can force our errors down to get some better information about them. Sound good? All right. So let's start with MDN. What does it have to say about the error object? It's pretty straightforward. We get instances of errors by instantiating them through the error function. We can pass a few things to it and get some interesting things out. Things we'd expect in any, modern language. The message, where it came from, and a stack trace about what was executing at the time. This is easy enough. Like, why are we even caring about this? Why did you guys invite me to talk? Because it's not that simple. It is not that simple. Ben Cisco says no. This is what the error object in the client side really looks like. It's terrible. These are all infuriating, despairing things that you'll encounter when trying to actually work with an error object across the browsers that real people use, not just latest Chrome. It will make you despair, and will make you feel like the whole internet is broken and nobody cares. So let's take a look. I got a little demo. So I have several demos today. They're all vanilla JS. I'm not doing anything fancy here. The only thing that I really bring in here is this little utility library that does something very boring and ugly, so I'm not going to bother showing you the code. It takes an object and an element and recursively prints every property on that object into it, just so we can see what's going on. In this case, I'm just going to create a new error object with a simple message, and I'm going to print out what that error looks like into the DOM, so we can take a look at it. Let's start with Firefox. Here's what the error object looks like. It looks pretty close to what MDN told us it was going to be, right? We have our name or message or file number, a line number, a column number, that's 0, which seems kind of weird, and a stack trace. So that's cool. Well, let's take a look at Chrome. What's Chrome look like? Well, that's not the same. That's not the same at all. it looks like Chrome treats the error object, particularly the stack trace, as like a catch-all of like all the information you're going to be is in this formatted string and nowhere else. There's the name of the error, error and example error, and the column and the line numbers are all in there. Whereas Firefox promoted those things to first-class properties on the object itself. All right, so I mean, all the information's there, so that's still fine, I guess. Well, what about Internet Explorer? So we look at Internet Explorer, and we get even less. We don't know what happened at all. We have a message. Unless you are very, very verbose with your error messages, I don't know that you could ever figure out where this one was coming from. Well, maybe there's some other magic going on here. Maybe throw does some things. So let's try like adding that. So in addition to just a plain old error, we're going to try throwing an error. And then we'll immediately catch it. And we'll just do the same thing, and we'll just print out its properties so we can compare the two. Let's print this out into JS error thrown. And this one will be a thrown error. Everybody see what I'm just doing? Okay. Oh. Thank you. So let's try again. All right, so now in Firefox we can compare a thrown and an unthrown error. And what's different? Apparently the act of throwing in Firefox generates a column number. I don't know why. It seems to me that the column number and the row number are, parallel concepts and should behave the same, but they don't. Let's take a look at Chrome. This is the most sane example today because they're exactly the same. Throw does actually nothing at all in Chrome. I have the exact same object. Does not change the behavior. But in Internet Explorer, an error is really a worthless thing until you throw it, because it's the act of throwing that generates the stack trace in Internet Explorer 11. So that's super, but notice that yet again, if you look at the stack trace in Chrome versus the stack trace in Internet Explorer, we have yet another format of what stack traces look like. So at this point, we might be a little confused. Or we might be a little freaked out. But it's going to get worse. So right along with the instabilities that occur in how browsers chose to implement the error object, there's differences in how they implemented their global error handler. So as Jamin alluded to in the previous talk, the simplest way to capture errors is just by attaching to the window on error. If a browser catches an error from your code and it doesn't know what else to do with it, it tries to pass it to this function. But every browser has a different shape of what an error looks like, and it has a little bit different behavior of what window on error does. So let's take a look at that. So here's another very simple example. And in this one, I'm just attaching a function to window on error, and I'm printing out whatever it happens to give us. And then I'm just globally throwing an error, just to make sure this whole thing blows up on me. So in Firefox, we take a look at it, and it's pretty worthless, huh? I get a global error happened in this file on line 31, which looks a lot like E is undefined scripts.js line 1. Well, what about Internet Explorer? Let it be said that Internet Explorer gives us more information than Firefox, because we got one more piece of information. We got the column number. I don't know what good a column number really does in debugging your error, but it's more information. Well, let's take a look at Chrome. Now, there's some magic happening here. There's something wonderful. Because you see, we get the basic stuff that we got before, the error, the line number, the column number of the file. But we also get that fifth property. We get the error itself, and with it, its stack trace. And that is amazing, and it's sad. It's amazing that we now, for the first time, have real stack traces and real errors simply by attaching to the global error handler. And it's sad because it took 15 years of browser technology to realize to pass the error to the global error handler. Why did it take so long to figure out, hey, maybe we should do this? That said, Chrome is awesome for doing that. I expect Firefox will catch up shortly. But we still have to deal with Internet Explorer. And we still have to deal with other random device-specific browsers. Definitely have to deal with IE 11, probably 10, unfortunately 9, I'm sorry 8, and I pity you 7. Ah! All right. So we talked about the JavaScript error object and the global error handler and how it was very inconsistently implemented across many different browsers. And note that all of those were the latest and greatest. That was latest Chrome, latest Firefox, and IE 11. We go back in time, that gets weirder and weirder and harder. So let's take a look at how errors move through JavaScript applications so we all have the same understanding of that. So here's a real simple example. At some point, the native code of the browser decides to invoke your function, your app, calls initialize, whatever, which calls other functions, and there's a whole stack of things that happen. And then at some point, an error happens, and it bubbles back up through the call stack, eventually landing on the native code. What does the native code do? Anybody know what the native code does? Window on error. Doesn't know what else to do with it. At that point, if it made it all the way back to the native code, nobody handled it. Baz didn't catch it, bar didn't catch it, foo didn't catch it. It bubbles all the way out to native. Native doesn't know what to do with it. Says, hey, is there anything here on window on error to catch this thing as a last resort? And we can see this in a demo. So here's another example, and this one's going to get a little longer. Let's start at the bottom. So I've attached a window on error handler that does the same thing before. Is I catch, the arguments that come in through window on error and I print them out. And I'm invoking a function called outer caller. Outer caller is I'm just trying to do something that resembles what a real live production app would do. Is it's calling an inline function. Maybe this is like a map or a filter or some sort of map reduce kind of function that does some business logic for you. And as part of that, we're calling with this function trigger error. Trigger error is the thing that actually triggers the error. On every step of the way, I'm try catching and printing out the properties of it and then rethrowing it, just so that we can see what the error looks like at each step. We can see what it looks like on the innermost trigger, inside the anonymous function, inside the outer caller, eventually landing on window on error. So here's that an example. The erroring function itself prints the error and traverses up through the inner caller and the outer caller, and then loses everything cool about it and drops on the global error handler. Note that we have the stack trace at each level. The stack trace isn't built as it traverses. The lowest level has the stack trace, and we can kind of reason about it a little bit here. So let's kind of compare this line by line. So here I have a stack going off on trigger error line 43. So what's happened at 43, we can see that's where the error is being thrown. But then something weird happens. We have 2 lines of outer caller here on 57 and 54. What's happening on those lines? 57 is the call to trigger error, and 54 is where we're invoking this inner function. Now Firefox, and all the other browsers as well, they don't know what to call this thing. There's a function here, and it's inside inner caller, but it doesn't have a name. It's an anonymous function. And anonymous functions, if you take one thing away from my talk, I want it to be this. Anonymous functions kill debuggability of your stack traces because you don't know what that function is. Anonymous functions get passed around. You don't know where they are when they get invoked a lot of the time. So it doesn't hurt at all to just give things names, like inner caller. Now we can reason about this much better. Inner caller is kind of a contrite example here. This could be, in the case of the React talk yesterday, this could have been filter out enter key presses as the name of this anonymous function that got passed in, or map one object onto another object. Using names for your functions gives you a better way to reason about what went wrong when you need to encounter a stack. We got something else weird happening here at the bottom. I got a couple just anonymous functions executing on lines 75 and 77. There's not a whole lot we can do about that. 75 is the original call, and 77 is my self-executing closure here. But if we wanted to, really be sure we had names, we can give a name to our self-executing closure as well. And now we can see that main executes outer caller, executes inner caller, executes trigger error. And this is a way better way to reason about what things went wrong in your application if you should encounter an error. But this is not that different from any other language, because we've just been talking about how synchronous JavaScript functions bubble errors between them when everything is running at the same time. But that's not where it's hard. The hard part about JavaScript is the asynchronous nature and callbacks. So let's try this again with callbacks. Your code at some point will invoke some native function. It was going to call add event listener, or it's going to call set interval, or it's going to call set timeout, and it's going to ask that native code that, hey, when something happens, call me back. Do this other thing for me. And then when that event happens, the native code, sure enough, will call that function you passed. But what happens when that function throws an error? What happens when your click handler dies for some reason because the user didn't enter the input you expected or for whatever reason? Well, a lot of the code that we write seems to expect that error is just going to bubble right back to foo. But it doesn't. When that native code picked it back up, foo wasn't executing anymore. Foo had long since been destroyed. And so the only place that the native code has to put it is to bring it back to window on error. And we can see this happening too. So here's an example that's starting to look a little bit more like a real application. This time I have an app, and my app has a few things on it. It's got an initialize function where I'm wiring up some click handlers. I have my click handler itself that in this case will generate an error. And then I built an application level on error handler. And I could use this to show the user a pop-up saying, oops, sorry, an error happened. Or maybe I want to AJAX these calls back to the server. Or whatever I want to do with a real error message or a real error object. And I want to make sure that I get errors into my application error handler. So I've just brute force wrapped my entire app in a try-catch handler, forcing errors to on error. And that should work, right? But just in case, we're going to attach a window on error handler. So we'll spin up the app and call initialize. So here's my app. I'm going to trigger an event, and it dies, and it hops right over my application error handler. That try-catch didn't catch it. It jumped right out of the on-click handler and went to the global handler. And we can see why right here in the stack trace, which you can't see when I highlight it. The only thing on the stack is on-click. The only thing there. Because it was the native code that invoked on-click. Initialize didn't invoke on-click. When we attached this event here, we ripped that on-click function out of our application and we passed it into the native code to call back. So when the native code receives this event and calls here, and the event throws out, it doesn't throw out into this try-catch. It's not there. It's somewhere else. It's embedded in the native code somewhere. This is what I like to think of as this asynchronous boundary that exists in JavaScript between things that attach events and things that receive events. And errors do not move across that asynchronous boundary by default. So, we talked about the browser error object, and we talked about the paths that it takes both through normal synchronous calls and through asynchronous calls. So now I want to try and address this problem specifically of this asynchronous this asynchronous boundary that the paths have to cross, and give one potential solution for how we can pass errors across it. So let's take a look at some code again. So I have a little helper that I wrote, and I'd like to get your thoughts on it. It's kind of terrible code, but it was the easiest thing to do to solve this particular problem. What I'm doing here is I'm monkey patching add event listener, and I'm adding some functionality to it. I'm capturing the original add event listener, and then I'm redefining it on every element. And the thing I'm adding to it is a third parameter. So in addition to saying, I want to listen to click events and get an on-click handler, I'm also passing in an on-air handler. That, hey, if you blow up, I want you to call me back with this function. And then the function that I pass in to the original add event listener isn't your callback function at all. It's a little anonymous one that I wrote right here that tries to invoke your callback. And if it fails, tries to pass it to your on-air function. And if not, it just behaves exactly as it would before. So if we add this to our little application here, what this gives us is by simply adding on-air to this line of code, our demo now behaves as we expect. And we get the error moving from where it was originally triggered directly to our application level error handler and not the global error handler. Now there's some garbage that got left over here. The stack trace is detecting this little trickery I played. So onClick is still on the stack, as well as this anonymous function that I had put in wrapped add event listener. Now, if we wanted to get more clever, we can get around this. But this is reflecting that I've kind of added some glue, this wrap event listener that's crossing that boundary for me and allowing me to pass these error objects back and forth. Now, this is a pretty crude example right here, where you would have to manually specify an on-air handler every time. But you could think about this in a way of, maybe for your application on a whole, you always want errors to go into a particular function. And so rather than listening to window on-air, you can just override base types to always have on-air functions. That does come with some risk. Not all browsers are as accepting of monkey patching host functions, but it's an option to consider. So, those were the three things that I wanted to talk about in general. But there's a bunch more context that we can talk about in terms of client-side error handling, and some things that I want you guys to know about. So, if you want to get more information about client-side error handling, there's a couple of libraries that you should really look at. First is Stacktrace.js. This has been around for quite some time, and this solves a particular problem. The thing that Stacktrace.js is trying to solve is to normalize the format of the stack trace. As we saw in the earlier example, every browser structured it a little bit differently. And that pattern will continue as we look into Opera, as we look into Android browser, as we look into other weird browsers. They all have a slightly different format of their stack trace. Stack trace will try and normalize that on the client side so that you can do some programmatic checking against it. The second is TraceKit, which is also open source out on GitHub. The goal of TraceKit is to get stack traces in situations or browsers where you normally wouldn't do it. and such as old versions of IE, or the only place that you have to catch the error is on window on error. And it does some very clever things where it looks at the source code of the JavaScript executing and computes using line numbers and column numbers and tries to guess a stack trace on your behalf. And it's pretty good at it. It's scarily good at it. The third thing is Zone.js, which isn't particularly to error handling, but it does provide some function here. This has come out of the Angular team, and I believe is a port of domains from Dart, is what somebody had told me at one point. But what it allows you to do is glue together those two sides of that asynchronous boundary and have some context of where was an event attached and where did an error happen, and get a consolidated stack trace across those. Using Zone.js, that is possible. And finally, Track.js is my commercial thing that you should look at some point, or talk to me later. So hopefully, we're all a little bit happier now about client-side. If you just add a little bit of extra work to your client-side code, we can stop worrying about errors and E is undefined, and just go back to building some awesome apps. That's all I got.